Let's look at what's under the hood of modern AI. We will trace the unbroken thread of mathematical logic, starting from the basic calculus you might remember from high school, all the way to the physical limits of dynamic unrolling in deep learning systems. So let's dive into the mechanics of modern differentiable systems. So, finding direction in a high-dimensional space. Let's start with our core objective. Training a neural network requires us to adjust millions and sometimes billions of parameters to minimize a loss function. In simple terms, we need to find the bottom of a massive multi-dimensional valley. To do this, the system needs one critical piece of instruction. Which way is down? How can we go as down as we possibly can? So that's where our training engine comes from. We need the gradient, which is a vector containing the partial derivatives of the loss with respect to every single parameter. But there is a challenge. Doing this analytically by hand is mathematically impossible at scale, and computing it blindly by guessing is way too computationally expensive. So we need a highly efficient automated engine. So the chain rule. It's the engine that runs on a single atomic mathematical reality. Complex functions are really just nested simple functions. Because of this, we can rely on the law of composition, which tells us that the derivative of a nested function is just the product of their individual derivatives. This gives us our universal formula. So the downstream gradient equals the upstream gradient multiplied by the local gradient. The key takeaway here is that every operation in a neural network, no matter how complex, ultimately breaks down into the single local multiplication. So how do we scale that single multiplication up to a massive neural network? This brings us to the Rumelhart's breakthrough. The chain rule can be seamlessly mapped onto a directed acyclic graph. Think of it in two phases. Phase 1, the forward pass, inputs cascade forward through elementary operations, computing and storing activations until they spit out the final loss. Then in phase 2, which is the backward pass begins. A loss joint initiates a backward cascade, taking that atomic chain rule we just talked about and multiplying the local gradient by the upstream gradients at every single junction all the way back to the start. So, now you might wonder why we compute gradients in this specific way. Let's look at the alternative. We could use numerical differentiation, but that scales poorly and gets trapped by round-off and truncation errors. We could use symbolic differentiation, like computer algebra, but that requires massive memory and suffers from expression swell, failing when it hits the algorithmic loop. This is why modern systems use automatic differentiation, or AD. It gives us exact derivatives with an overhead that is just a small constant factor of the forward pass. Its only primary defect is that it requires tape memory, meaning it has to store all the forward states. So, reverse mode AD operates like a tape recorder. To really visualize the AD, think of it as a mechanical tape recorder. So during the forward pass, the system unspools the tape, recording every single intermediary state and mechanical operation. This the trade-off is space and complexity. we must physically record these states in memory. But the magic happens in the reverse mode. The system spools the tape backward, reading those recorded states to compute derivatives at scale machine precision, bounding the computational cost to a tiny fraction of the original function. So, the architectural shift in graph building. Historically, building these graphs involved define and run a static approach. Like think of an old factory assembly line. The blueprint was locked, compiled first, and executed second. It was rigid and very difficult to debug. But we had a massive architectural shift to dynamic graphs, specifically popularized by PyTorch. This is defined by run paradigm. Here the code is the graph. The blueprint is actually live and constructed dynamically at runtime, allowing for highly intuitive control flow. And now let's look at PyTorch Autograd in action. As you execute the basic math, like y equals w times x and z is y plus b, the forward pass is dynamically building computational graph in memory. Every operation spawns a node that records exactly what happened and stores the specific function required to compute its gradient later. Then you simply call z.backward. The system consumes that recorded graph, immediately back propagating the joints back to the leaf tensors. So, because this graph is built as the code executes, we achieve fully differentiable programming. Native Python control flow like if statements and while loops becomes natively differentiable. But this creates a fascinating temporal illusion, the Autograd engine. Um, to wit, a loop is not a black box, it is just a deeply stacked neural network generated in real time. The major implication here is that if you run, let's say, 1,000-step iterative sequence, like a long physical simulation or a BSD march, you are actually creating an unbroken 1,000-layer deep computation graph. So, the mathematical consequence of that deep iteration to transport an error backward from step t all the way to step k, the gradient must pass through sequentially connected nodes. At each step, the gradient is multiplied by the local Jacobian matrix, but there is a huge danger with continuous multiplication. Just as multiplying scalar by 1.1 100 times causes it to explode to infinity. Multiplying hundreds of Jacobian matrices guarantees numerical instability. So we need to end up crossing an eigenvalue boundary. If the largest eigenvalue of these matrices is less than 1, we get vanishing gradients. The long-term temporal components shrink to 0, and our model develops amnesia, so unable to correlate distant events. But if the largest eigenvalue is greater than 1, we get exploding gradients. The gradient norm grows exponentially, exceeding floating point limits, turning into null values, and completely destroying the training process. With unbounded and non-linear sequences, hitting this boundary is practically a statistical inevitability. Geometrically looking, what does an exploding gradient look like? It looks like literal like a wall. The curvature explodes simultaneously with the gradient. So the consequence, as you can see, is catastrophic. When standard gradient descent encounters this wall, the massive gradient norm forces a colossal step. The optimizer violently overshoots, jumping entirely out of the local valley and destroying sometimes days or hours of learned weights. So, how do we survive this? We introduce gradient clipping. The algorithm is quite simple. If the norm of the gradient exceeds a threshold we set, we call it theta, we rescale it to have a norm exactly theta while perfectly preserving its direction. So why does this work? Because it ignores the massive exploding or explosive magnitude generated by the wall, but it completely trusts the direction. By bounding the step size, it allows the optimizer to safely traverse to steep curvature without detonating in the long run. So, let's recap. We started with the math, composing derivative with the chain rule. This enables our paradigm reverse mode AD for exact scaling. This is implemented in software using, for example, PyTorch, Autograd, to dynamically building graphs. The consequence is that loops become deep and stable networks. And finally, the control mechanism. Gradient clipping acts as the required pressure valve to keep the system stable. So the final insight to leave with you is, like, the magic of modern deep learning isn't just magic. It's simply the flawless execution and boundary management of the fundamental calculus at a high scale.